Okay, so today we're going to look at our last type of algebraic limit, which is limits at infinity. And to do this, we're going to revisit the basic reciprocal function, which you've seen before, and you remember looks like this. And of course, so this is a discontinuous function. And of course, we hopefully remember that we have a horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals 0, right? These lines are down here. And if you recall from MHF, when we spoke about the end behavior of the function, right, we would have said that as x approaches infinity, f of x approaches 0, right? Technically, we would have even said from above. And as x approaches negative infinity, f of x approaches 0 from below. Okay, well, if we consider this now as a limit, we could also say then that the limit as x approaches infinity of 1 over x equals 0. Yes, it's really only a one-sided limit. It doesn't really have both sides. It doesn't really have the side from the right, but it's still definitely, this is sort of a special case, and it is a limit. And we could also say then as well that the limit as x approaches negative infinity of 1 over x also equals 0. Okay, and this leads us to our theorem for limits at infinity. So if you can just pause the video and then write this down, that would be great. Okay, so if f of x is a function where the limit of the function as x approaches infinity equals infinity, then it would be true that the limit as x approaches infinity of some value k, any real number, over f of x would equal 0. And the same is true for negative infinity. So let's take a look at what that looks like. Okay, and so technically, we don't really use substitution to evaluate limits at infinity, but in general, we can sort of think by substitution that any number, anytime, over infinity will always give us 0. Okay, so if we use that principle to look at these limits, we see here that we have the limit as x approaches infinity of 4 over x squared, so that's like 4 over infinity squared, and hopefully we can see then that that limit would equal 0. Okay, same is true for this one over here. Okay, again, we have a number, 42, negative 42, over, if we're plugging infinity into the bottom there, we have sort of a giant value on the bottom, and so that limit, that's going to get really, really close to 0, okay? Please note these are not indeterminate limits. These are not 0 over 0 or anything of the sort, but in general, that's the idea. And just to emphasize that and make sure that you do understand that, remember that the limit as x approaches infinity of something like x squared would be infinity, right? So when we take a k value and we put it over that, we get a limit of 0. Okay, so what would happen then in a case like this? So again, if we start with always thinking about substitution, then we look at this one and we think, oh, we're going to get about infinity on the top and we're going to get infinity on the bottom. And so this, in fact, is sort of another indeterminate form. This gives us infinity over infinity by substitution. Okay, and so then we need a method to deal with it. And actually the method for this one, you actually know what the end behavior of this function looks like, if you recall back to advanced functions already. And so the method for this one is, in fact, what we do is we divide all the terms by the highest power of x. Okay, and I'm going to show you what that looks like. So here we're going to take the limit as x approaches infinity. Our highest power of x here is an x to the 1. So we're going to take every single term and we're going to divide it by x. Okay, and when we do just a little bit of simplifying, we see that over here we just get 3. Here we get a 2 over x, nothing you can do to simplify that. Here we get a 4, and here we get a 9 over x. And now, if we take that limit by substitution, by substituting in infinity, I think you can see how this term, the limit as x approaches infinity, goes to 0, and this term, the limit as x approaches infinity, goes to 0, and by substitution, we're simply left with 3/4. Now, I hope you can see that this is very similar to finding the horizontal asymptote from advanced functions. Remember that if you look at the original question, the degree of the numerator is the same as the degree of the denominator, and so we take the leading coefficient of both. Okay, and so that is the limit, as x approaches infinity. Okay, I'd like you to pause the video and try the second one to the right there. Okay, highest power in this case is x squared, so I'm dividing every single term by x squared, and that simplifies to the limit as x approaches infinity of 3 over x plus 4 over x squared on the top, and on the bottom I get a 1 plus a 7 over x minus a 7 over x squared. And again, if I now take this limit by substitution, this goes to 0, this goes to 0, this goes to 0, this goes to 0, and I am simply left with 0 over 1, which is 0. Again, horizontal asymptote, the limit as x approaches infinity from advanced functions. Degree of the numerator is less than the degree of the denominator, and so the horizontal asymptote is 0. Okay, now before I move to the next slide, well, I am going to move to the next slide, I'd like you to think about this one for a minute. I'd like you to try the same process and pause the video and see if you can get this right, and try to relate your thinking back to advanced functions. Okay, I hope you got to that point right there. And again, as we take that limit as x approaches infinity, we're going to get 0, we're going to get 0, we're going to get 0. And so by substitution, we get 3 over 0. And that limit equals, it's undefined, and therefore the limit equals infinity. Now I want you to relate this back to advanced functions. Degree of the numerator is greater than the degree of the denominator, and that of course creates an oblique asymptote, and that is why the limit equals infinity. Okay, so there's a practice sheet in this same folder that has a combination of limits in infinity and algebraic limits, and that's sort of your practice to make sure that you can do all of these algebraic limits together. Okay, thanks.